Let's go ahead with the next talk. Next talk will be by Srijita Sinha. Is going to talk on perturbation in a dark energy model. Srijita. Srijita,
is it? Yeah. My screen is visible.
Yes. Yes.
Okay.
Okay. Go ahead.
Thank you. Good morning. And firstly,
you have 12 plus 13 minutes. I will warn you before 2 minutes. Okay. Sorry.
Plus 3, Rajesh.
Yeah. 12 plus 3.
Okay, sir. So firstly, I want to thank all the organizers for providing me with the opportunity to present my work here in CS GAC 2022. The title of my talk is Perturbation in a Dark Energy Model. Now, we know that the standard model of cosmology is based on the cosmological principle. The cosmological principle states that on a sufficiently large scale, the universe is specially homogeneous and isotropic. And now, how large is sufficiently large? It is larger than the large-scale structures like the galaxy clusters and the galaxy superclusters. Now, as we start zooming in on some smaller scales, we start seeing the inhomogeneities, that is the galaxies. These large-scale structures have evolved from some initial density fluctuations. Thus, for any cosmological model giving the evolution of the universe, it is important to successfully produce the large-scale structure. For our work, we have considered a specially flat metric as well, given by the famous Robertson-Walker metric, that is t square equals minus dt square plus a square dx square plus dy square plus dc square, where t is the cosmic time and x, y, and z are the co-moving spatial coordinates, and a being the scale factor, which accounts for the time evolution of the spatial hypersurface and is scaled to be 1 at the present epoch. Now, from the recent observation, we know that the universe at the present epoch is expanding with an acceleration. And any matter component giving rise to the recent acceleration is called dark energy. Now, both dark energy and dark matter are evolving together from the beginning of the universe. Hence, an interaction between them cannot be ruled out a priori. This naturally raises the question, when is the interaction significant in the evolution history of the universe? That is, if the interaction was there from the beginning of the universe and exists through its evolution, or the interaction is a recent phenomenon, or the interaction was entirely an early phenomenon and not at all present today. And a modification of the interaction coupling parameter in the interaction term may answer this question. So the motivation of this work is to assess for any preferable stage of evolution when the interaction is significant. For our work, we have considered both the dark matter and the dark energy to obey the perfect fluid distribution. In presence of any non-gravitational interaction, these fluids do not conserve independently, and there is an energy flow between the two, where Q is the amount of energy transferred. WdE is the equation of state parameter of dark energy. Now, when Q is greater than 0, energy is transferred from dark matter to dark energy, whereas for Q less than 0, it is being transferred from dark energy to dark matter. For our work, we have considered W dark energy to be parameterized as the CPL parameterization, and Q is proportional to rho dark energy, which is the energy density of dark energy, and a coupling parameter beta, which is a function of the scale factor A, and curly H, which is the Hubble parameter in conformal time. And this equation, that is rho prime, this prime is the time derivative with respect to the conformal time. Now, for the answers of the coupling parameter beta, we have considered 3 cases. The case for where the interaction is significant at some later time and is denoted as model L. And the next parameterization is such that the interaction is significant at some earlier time and is denoted as model E or model RD. And the third one is where the coupling parameter, that is beta, is constant throughout the evolution history of the universe. Now, in this right-hand side, we have shown that the dimensionless energy transfer for model late and model constant, that is where beta is a constant, are almost similar. The late time evolution is almost similar, whereas for model E, the interaction is there for a brief period of time in the past. We have considered the energy flow from dark matter to dark energy, and hence beta 0 is positive. And the values of W0 and W1 are such that W dark energy is always in the non-phantom region, that is W dark energy is greater than -1. For the perturbations, we have considered the synchronous gauge, where psi and E are the synchronous gauge fields, and on writing the density fluctuations as delta C for dark matter and delta DE for dark energy, and the three velocity perturbation as VC and V dark energy, and defining the effective sound speed in the rest frame of dark energy as CA squared, we have obtained the perturbation or energy momentum conservation equation. Perturbation in the energy momentum conservation equation, and we have solved this equation using adiabatic initial conditions in CAMP to avoid any early time instabilities due to pressure perturbation. We have used CA square equals 1, and in this plot we have shown this left hand side plot, we have shown the evolution of matter density contrast, where matter means both cold dark matter and baryonic matter. With respect to the scale factor A. We have also plotted delta M for the lambda CDM model, and for a clear understanding, we have scaled delta M for all the models with that of lambda CDM model at the present epoch. And the lower panel shows the fractional change in delta M, that is delta M lambda CDM minus delta M by delta M lambda CDM. So we can see from this left hand side plot that model E and the lambda CDM model are very close, whereas there is a difference in delta M for model C and model L. And the interesting part in delta dark energy is that delta dark energy fluctuation decays at the present time, but decays to a very small value, 0 for model E, which is the model early, and the evolution of delta dark energy for model E and model C are similar at earlier time, whereas model L and model C are similar at late time. We have also computed the temperature power spectrum and the matter power spectrum. Here, the lower panel shows the fractional changes. L is a multiple moment and K is the wave number. Here also we can see that model E, that is where the interaction is significant at some early time, behaves closely to the lambda CDM model. The same thing is true for the growth rate and F segment, where growth rate is the logarithmic derivative of delta M with respect to the scale factor A. We have plotted that with Z redshift at the present epoch. We can see the difference between lambda CDM model and model E is negligible, whereas model L and model C, that is late interaction and constant coupling parameter, has a significant difference. The difference between model E, that is model early, where the interaction is significant at some earlier time, and lambda CDM model is there only when there is the interaction, that is at some brief period earlier. So with this, up to this much, we can say that model E behaves closely to the lambda CDM model. Now we have constrained these models with some recent observational data sets. For that, we have considered the 6-parameter lambda CDM model along with the 3 model parameters, and the priors are the standard priors for the lambda CDM model. But for the model parameters, we have made beta 0 unconstrained and put the prior on W0 and W1 such that W dark energy is always greater than -1. The data sets used are the recent CMP 2081 collaboration data, BAO data, and the supernova latest Pantheon catalog for the type 1 and supernova data, and the F sigmoid compilation by Nesseris et al. This is the RSD dataset, where omega m is the corresponding fiducial cosmology used to convert redshift to distance. Now, from the perturbation analysis, we have seen that model E, that is where the interaction exists at some early time, behaves closely to the lambda CDM model. So we will discuss the observational constraint on model E first, and then we will just compare all the three models. So this is a one-dimensional marginalized values at 1 sigma error bar for model E for all the data sets. Here we can see that the interaction parameter beta is greater than 0 for all the parameter data set considered. That is, energy flows from dark matter to dark energy. And for Planck data, beta 0 equals 0 lies within the 1 sigma error region, whereas for other data sets, beta 0 lies outside the 1 sigma error region. And W0 and W1 remains unconstrained. We have also shown the values for the derived parameters omega H0, omega m, and sigma 8. H0 is the Hubble parameter at the present epoch. For the Planck data, the central value of H0 is very small, whereas sigma 8 is around that obtained from the galaxy cluster value, that is 0.77. So we have added the RST data. And on adding all the data sets, the values, central values, moves towards that obtained from the lambda CDM model, and the error bars also decreases. So for this is the plot where it shows the correlation between the different parameters for model E. And for the comparison between model L, model E, and model C, we have only considered the Planck data, because on adding the different data sets, the changes are similar. That is, for model L and model C, the central values are very close to each other and is significantly different from model E. Beta for the central value of beta 0 is very small for model L and model C. And the central value of H0 is also small for model L and model C. But on adding all the data sets, the central values shifts towards the lambda CDM model for all the three models. So we haven't shown those. Now for the conclusion part, we can say that from the growth rate and the evolution of density perturbation and the CMB temperature spectrum, matter power spectrum, we can say that model E behaves closely as the lambda CDM model. Thus, we can say that model E is better than model L, where the interaction is significant at some late time, and model C, where the interact coupling parameter is constant. Thus, we can conclude that the interaction, if present, is likely to be significant at some early stage of evolution of the universe. And thank you.
Okay, thank you, Srijita, for finishing it in time. So now it is open for questions. Sriram, go ahead.
Hi, Srijita. Thank you for a nice talk. I was wondering whether, which data picks better, this evolution history, number one. And number two, with the Planck data alone, your H0 is going down considerably, causing more tension.
Yes, sir. I think, this is mainly, I think, because of the answers I used for beta. Maybe I should have checked other parameterization, and as well as, at the constraint, prior constraint of the prior, I put on W0 and W1. On changing them might help.
Okay, and you have allowed for, maybe I missed this, you have allowed for the perturbations. You included the effects of the perturbations, yes, for instance, on the integrated Sachs-Wolf and so on, or in the dark energy.
Yes. I have included all the perturbations there.
Okay, I understand. And you are saying that, the omega 1, or rather omega naught, which, it seems to suggest it is very close to lambda, correct?
Yes, it is very close to lambda, but I put the deliberate constraint that they won't cross -1. Maybe on relaxing that might help.
No, I am not interested in going phantom, if that is, that is not what I meant. But I have a very naive question. If it is close to the cosmological constant, can there still be an interaction?
Oh, yeah, actually, it can be said that at present there shouldn't be
There
any
is no.
interaction.
Okay.
Anyway,
Okay.
that is what
Okay.
also we are trying to say.
I understand. I have some other questions. I'll
Yes.
speak to you later. Thank you.
Okay, sir. Okay, sir. Thank you.
Hi, Srijita. I have a question. Can I ask?
Yes. Yes.
So you have compared the Planck results in the next slide, right? Have you
Yes.
seen that with Planck plus BO plus Pantheon and all? Like.
Yeah, yes, of course I did, but I just only compared Planck because on adding, look, the way these parameter values are shifting, it will be same for all the three of them. I mean, the central values will change.
I was looking about the parameters. So the observable parameters here, H naught omega m, right?
Yeah.
So when you are taking Planck data plus BO data plus FS8, right?
Yes.
Up to that slide.
Yeah.
So here the parameters are more or less, they are better than when you are just taking Planck, right?
Yes.
So if you have compared them, have you got the same result or is it different?
Yeah. I mean, for model E and model C, for model L and model C, you are asking?
Yeah.
Yes. Or the way this model E changes, like it's 64.12, which is quite less and far away from what we get from Planck. But on adding F sigmoid and PAO, it changes towards the lambda CDM value. The same happens for the other two models as well. It is changing in the same way, like from 63, which I think is 63. Yeah, it will be from 63 to it will go to like 67 point something. That is closer to the lambda CDM value for what we obtained from the lambda CDM model using the Planck data only. So the change is similar. So that's why I haven't.
Okay, sure. Okay, thank you.
Thank you.
Okay. Are there any more questions? Okay. If there are no questions, thank you, Srijita, for a nice talk.
Thank you, sir.
Let's